Okay, so I wanted to review some of the student answers to the term test that had at least the right idea behind them. So in this question, this is from version 2 of the midterm. So this is the second section. And but both sections were actually given the same Cayley diagram. In this piece of artwork, from the Bridges 2024 conference. You can look it up. He actually used much prettier colors, but they weren't high enough contrast for the printer. So I used two different kinds of contrast for the printer. So anyways, but they turned out to be the same group. Now, in the first part of this version, you're asked to write the elements of G as a permutation. And we know that we can do that from Cayley's theorem. And one of the things that visual group theory does when proving Cayley's theorem is it gives a step-by-step procedure for turning any group into a set of permutations by using the Cayley table. And that was one of the things that I had reminded you to review when we talked about Cayley's theorem. So in this case, this student did a good job of doing the setup here. They thought about 8 points, and they said there will be 8 rows, so we have 8 solutions. For example, if the table is 1, 2, 3, 4, 5, 6, 7, 8, and then in row 2, they noticed that there was a permutation that occurred. So for example, instead of position 1, let me just highlight it here. Okay, so instead of position 1, there is a number 2. And in place of position 2, there is a 4. In place of position 3, there is a position 5. So we indicate that by 1 goes to 2, because in position 1 there's a 2. In position 2, there's a 4. In position 3, there's a 5. In position 4, there's a 6. And in position 5, there's a 7. Okay, now there's actually a few different ways to signify this as a permutation. You could have almost done the opposite permutation and that would have still worked, but anyways, this procedure will work. This student just didn't fill in the rest of it, and it actually, once you get started, it's not too bad, especially since there are a lot of patterns in this particular diagram. Okay, so I'm gonna just move this up. And the second part was one of the things that was kind of disappointing to me here. What was the name of the natural operation on the set of permutations? This is one of the questions that we did in both sections, as a poll question even, because a lot of people couldn't do it. So how do we put permutations together? I mean, probably the best way of describing it is as the composition of permutations or concatenation of permutations. Okay, so it's like a composition of some sort. Okay, and we talked about that in class, so that was a little disappointing for your poor professor. Okay, now in part C, the question was determine if you can construct an embedding from G to this product. And then if you could do it, determine what that embedding is, and if you cannot, then say why. Okay, so let me grab a student solution for this one. I may be popping in the wrong one because they're of course kind of small. Here we go. Now, this student didn't quite get there, but got almost all the way. So they said, no, we observe the multiplication of G. In the multiplication of G, there's no symmetric along the main diagonal. So G is not abelian. Okay, so that's correct. That's a correct statement. C3 and C5 are both cyclic groups, so they're also abelian. Okay, so that's correct. If G is not an abelian group, then phi of G is also not an abelian group. But C3 cross C5 is an abelian group, which is a contradiction. Okay, so have we proven that you cannot have an embedding of an abelian group inside of a non-abelian group? Well, one of the problems with this response is that, for example, well, basically we haven't proven it. That's one of the issues. So can you prove it? Now, like a lot of contradictions, if you want to prove it false, or prove that this sort of thing doesn't exist, this approach like used properties or compared properties, which is great, which is a great strategy. Another strategy that you can use is to compare orders, because we have a lot of like divisional issues, right? So if we have an embedding, then the order of G has to interact with the order of C3 cross C5 in a certain way. Okay, so if we take it approaching orders, which is kind of the way that I thought of it, now we know the order of G is equal to 8, and the order of C3 cross C5 is equal to 15. So if it's an embedding, that means that it's a map with kernel 0. And so the order of the image of this map is going to be equal to the order of G. And so that's going to equal 8. But 8 does not divide 15. And that is what would be required in order for us to actually get an embedding, right? Because we need it to lie within C3 cross C5. So there is not an embedding by, say, Lagrange. Okay. So oftentimes when I'm thinking about maps or comparing two groups, we can think properties and we can also think orders. Okay, so that was the first option in this question. The second option was question 16 or 17, and we had this cycle graph. Most students chose to do this one, and most students got the first couple of questions right. So I'll just go through this briefly. The order of this group was 9 by counting the dots, and then Lagrange's theorem just gives us 1, 3, and 9 as the orders of the possible subgroups. So then the next part was not done as well, because this one asked whether the group had at least one subgroup of each order. So let's again see what the sample student solution is. Okay. So this is a really good solution. So it says, see from the cycle graph that that G has 4 subgroups of order 3 where each orbit forms a cycle of order 3. Okay, so this is really good because it doesn't just say we can see it has 4 subgroups of order 3, but it tells us how we form them. Okay, so that's a really good thing. A lot of people didn't say how they were formed. And then, of course, the entire, I wouldn't say the entire graph, I would say group itself is its own improper subgroup, or just subgroup of order 9, and E is the trivial subgroup. Okay, so that's great. And we know that it is an abelian group. If we're told that it's an abelian group, then we can figure out what group it is. Actually, you don't need to be told it's an abelian group, but I gave you that hint because we haven't done a lot of like kind of narrowing down exactly what a group is according to its properties yet. So I think I put a solution of this one in. Let me see if I have it here. Okay, so no, I don't have that one. Okay, maybe I didn't put one for that in. Let me just see. No, I did not put one for that in. But yeah, so it's a group of order 9, and it's an abelian group of order 9. So you have options of either just having it to be C9 or C3 cross C3. And so you have to determine which one it is from that information. Okay, and then sketch a Hasse diagram that shows all of the subgroups of G. And so this is the diagram that the student came up with. This is a great diagram because we know that all of these are of order 3, as the student notes. They all lie inside G, and they all contain the order E. They all contain the subgroup E. Now, maybe the thing that I might add there is some kind of generating bars to indicate the subgroup and not just the element E. And then the other thing I would add here, of course, is generating bars, because these usually denote elements themselves. Okay, but I think the spirit is very good. The other thing the student didn't really do, I was scrolling up. Maybe on their test they defined what the R's are, but you'll want to make sure that you define exactly what the R's are. Okay, so that is a good Hasse diagram. Okay, in the making connections section of this test, you were dealt the double planetoid, and because this test was getting long in terms of space, I cut it out at the last minute. This is what it looked like. Okay, and we're told this nice quote by Escher. If you did not read it, if you did not have this test, I encourage you to pause and read it because it's very relevant to Part B. So there is the tetrahedron. Now, the symmetry was done quite well. Most people were able to describe one symmetry of this double planetoid. Now, I graded Part B, and this is one of the places where reflections were not very well done. Some people were just trying to give me some explicit homomorphism related to this shape in terms of algebra, and kind of missed the whole point of Escher describing through his work as an artist. The artist statement was really clear, here, right? So what kind of isomorphism, using our idea of an isomorphism, what does that mean intuitively, and how is that related to this? This is what I was looking for. So there were several great student responses to this. So here's one. An isomorphism describes two exact objects with the only difference being the names. Escher depicts two similar tetrahedrons, but both have different descriptions. Escher shows that there is a homomorphism between tetrahedrons, but they aren't exactly the same. This is how Escher describes an isomorphism between double planetoids, human to natural. Yeah. Okay, so the student kind of points out that, isomorphisms actually have to be exactly the same. Do we really want to say that in our world here that these are exactly the same? Maybe not. Are we saying the surface is exactly the same, or are we saying the underlying shape is exactly the same? Okay, but they're getting the correspondence between human and natural, and that's really clear in the quote, right? The light-colored one is inhabited by human beings who have completely transformed their region into a complex of houses, bridges, and roads. The darker tetrahedron has remained in its natural state. The two bodies fit together and make a whole, but they have no knowledge of each other. So we have one that's developing in one way, and we have another developing along a totally different trajectory. Okay. I think I grabbed another student's answer as well. That's the same one. Let's try grab another one. Let's see. Okay, maybe I did not grab another one. Oh, here we are. Here's one. Humans have isolated. Oops. Humans have isolated themselves from nature through houses and bridges and roads, creating a new world. And this world is isomorphic to the world where plants and animals live. We have separated ourselves from nature, even though we all live on one earth. Okay, so this student emphasizes the separation. Okay, so any of these are fine. Like kind of just the correspondence between humans and animals is important here. Kind of these two tetrahedron communicating similarity. And this is I guess a theme, I would say, of algebra is mapping two things that are similar, especially in terms of symmetry, to each other and finding commonality, right? Like deciding what to see and what to ignore. And it's also something that we see in artists, right? What do they see and what do they ignore? What do they choose to focus on and what do you choose to ignore? And so these two kind of concepts unite math and art. Okay, the order of the symmetry group of a single tetrahedron is 24. What is a symmetry group of a single tetrahedron? How do you know? Okay, so we're told the order of the group, and we want to find the total symmetry group. And there was a hint going back to A. So I'm going to scroll back to A and just look at the wording of the question. Let me move this. Okay. So the wording of the question, the relevant part here, was to describe the permutation on the vertices as well as the physical action. So that permutation on the vertices is maybe a novel part. And what I meant by that is if you have a tetrahedron with 4 vertices, you're going to get some sort of permutation on them whenever you do a symmetry action. And in particular, the symmetry actions are in correspondence with at least certain permutations. Okay, so permutations correspond to symmetry actions quite directly. Okay, and so we're told to, and this is all in a single tetrahedron, even though the beginning was on a double tetrahedron. So in the first part, so let me go to a student solution before I explain it anymore. We'll see where we are. Oops. Okay, so this student points out that we permuted the vertices, and there are 24 different orderings of the vertices, so that means that we have to get all of them because of the order of the symmetry group. And then they also point out truncated tetrahedron describes the vertice permutations perfectly. Okay, so this part is something that's kind of in the textbook. We don't really need to worry about that. Maybe they were trying to relate it, but in any case, we focus on this other part. And so this is like the order of the symmetry group must be greater than or equal to 24 by the vertice exchange. But then we know, it must be less than or equal to 24 by the vertex exchange, right? Because then it's contained inside of S4. Actually, you know what? You can argue it either way. With the vertex exchange, it's greater than or equal to, is less than or equal to by vertex exchange. I should say equal to, because you can phrase it either way. Okay, basically just state it directly like the student did. Okay, and then part D was done well as well. Okay, so I think that is as far as I'm going to go with version 2. And there will also be another video with version 1 coming up as well.